In Chapter 5, we're going to take a look at probability, random variables, and probability distributions. In Section 1, we're going to take a look at simulations and then just some basic probability rules. So one thing that's really important to probability is the idea of randomness. So if you think of rock, paper, scissors, coin tosses, the lottery, casinos, any game involving dice, spinners, or cards, those all involve randomness. Even traits we inherit, such as gender, hair and eye color, blood type, dimples, they're all determined by the chance involved in which genes get passed along. So all of these represent something we call chance behavior, which we can understand and work with. So the outcomes are governed by chance, but in many repetitions, a pattern emerges. And that's how we get probabilities, is with that pattern that emerges after many repetitions. So a key thing about here is, that's what probability is, the regular patterns of chance behavior, is that you have to have many repetitions. So the definition of probability, so let's go over chance behavior is unpredictable in the short run, but has a regular and predictable pattern in the long run. So it's kind of thinking about how if you could flip a coin 3 times, it could come up heads every time, but we know there's a 50-50 shot of flipping heads or tails. That's because in the long run, there's the predictable pattern that the probability of flipping heads or tails is 50-50. So there's 2 types of probability that we use to describe chance. The first one is empirical probability, and the second one is theoretical. So empirical probability and I'm going to abbreviate probability here, is based on actual observations. If you flip a coin 500 times, you flip a coin 500 times, you get heads 489 times, the empirical probability is 489 out of 500. It's the actual number of heads you got in flipping a coin 500 times. On the other hand, theoretical probability is empirical probability based on an infinite number of trials. So this goes back to that flipping a coin. So we'd expect that out of an infinite number of flips, half of them should land on heads. So the theoretical probability is 0.5. So it goes back to the example I was just talking about, how, in a specific number of flips, heads might come up, 489 times, but we know that theoretically, the probability is still 0.5. So there are 4 key terms that we're going to see a lot when we're discussing probability. So the first one is random event. So a random event is an activity with a measurable result. So like flipping heads could be my random event, a coin landing on heads. The outcome is the result of one trial of one random event. So if I'm looking at a coin landing on heads, I flip that coin. The outcome is if it lands on heads or if it lands on tens. An event is a set of related outcomes. And then the sample space is the set of all possible outcomes. So going back to that flipping coins one, the sample space is going to be heads or tails. Those are the only outcomes you can get when flipping a coin. If we're rolling a six-sided die, all of our outcomes, our sample space is 1, 2, 3, 4, 5, 6, because those are all of the outcomes you can get. So depending on what your event is, that determines what your sample space is. We usually call a sample space just with a capital S. You'll see that a lot. So let's talk about finding probability. So the simple basic definition of probability is that it's the number of outcomes in the event divided by the number of outcomes in the sample space. So we usually denote probability with a capital P, and then in parentheses E is the probability of the event. So equals the number of outcomes in the event all over our sample space. And I know this looks like a D, but it's a P. Okay. Key thing in this formula, all of the outcomes in the sample space have to be equally likely. So you're going to see a lot of terms like a fair six-sided die or a fair coin. Just means that landing on heads or tails is equal chance, landing on any six numbers equally. It's not a trick coin or a weighted die. So let's take a look at an example. We have that a bag contains 10 marbles. There's 2 black, 3 blue, 1 red, and 4 white. We want to find the following probability. So the first is the probability of pulling out a black marble. So if we look, our number of outcomes in the event. So if we look, there are 2 black marbles out of my entire sample space, which there are 10 marbles. And so our probability is 2 out of 10. And anytime you have a probability that can simplify, you're going to want to do that. So 2 out of 10 is 1/5. So there's a 1 in 5 chance. If you want to think about it in terms of probability, that's 20%. So there's 20% chance that if you draw a marble, it's black. Second example we're going to look at is the probability of pulling out a red marble. So if we look, there is 1 red marble out of our total 10, which 1 out of 10 doesn't simplify, so that'd be our final answer. If you want to think about it in terms of percentages, that's a 10% chance. So you can also say, you know, which one is more likely to happen. You're more likely out of the two to get a black marble than you are to get a red marble. So let's take a look at an example with dice. So 2 dice are rolled and the sum of the pips is noted. So the little dots on die are called pips. We want to know the probability that a sum of 9 is rolled. So this gets a little bit tricky because we're rolling 2 dice and we have to think about all of the different sums you can get when you're rolling 2 dice. So I'm going to draw a little table here. So I'm going to call this first row a single dice. It's called a die. And then this one is going to be die 2. Do it this way. so we can get out 1, 2, 3, 4. Ooh, bad lines. 1, 2, 3, 4, 5, 6. Same thing happens with die 2. So what I can do is for each row and column, add the 2 die. So like if die 1 is a 1, die 2 is a 1, their sum is 2. Do this in a different color. Okay, if I get a 2 and a 1, their sum is 3. So then you just keep moving across. Then what if the first die is a 1, but the second one is 2? So you can see there's a pattern forming. So it makes sense. The smallest sum on the die is 2. Biggest sum is 12, because that's 2 6s. So I want the probability of getting a sum of 9. So I'm going to go through here. I'm going to highlight all of my 9s. So when I write this out, I'm going to write probability sum of 9 equals. Okay, so I highlighted 4 9s. Okay, so that's the number of outcomes in my sample space over my complete sample space. So I have a 6 by 6 row and column, so out of 36, and 4 over 36 can simplify to 1/9. So there's a 1 in 9 chance that if I roll 2 dice, it comes out as their sum being 9. You can also notice diagonally in the table there's a pattern. There's a lot of patterns in the table, but if you also look, the most likely thing to roll is a 7, because 6 of our outcomes are 7. So if you're going to roll 2 dice, it's very likely that those 2 die come out as adding to 7. Okay. So in example 3, we are flipping a coin 3 times, and then the results of each flip are noted. And we want to know the probability that exactly one of the flips results in heads. So what it would be good to do first is list all of our possible outcomes. So obviously all 3 coin tosses could come up heads. They could all 3 come up tails. We could get heads, heads, tails, heads, tails, tails. We could get head, tails, heads. There's tail, heads, heads. Tail, tail, heads. Tail, heads, tails. Should be 9. 1, 2, 3, 4, 5, 6. Sorry, 8. 8 outcomes. So that's all of the different outcomes you could get in flipping 3 coins. Okay. So the probability of getting, so we want to know of those 3 flips. So 3 flips is considered one out, like one set, one event. We want that in those 3 times, exactly one of the flips results in a heads. So we want 1 head. So we have a total of 8 outcomes. So I'm looking 3 heads, 3 tails, 2 heads and a tails. There's heads, tails, tails. There's also tails, tails, heads, and tails, head, tails. So those are the only outcomes we had that resulted in one being heads. So that's a probability of 3/8. Okay. On the reverse side of things, we can look at the probability that at least one of the flips results in heads. So as long as there's at least one heads, we can consider it one of our outcomes. So that's a probability one or more heads. You can also write it as at least one head. So we still have 8 as our total possible outcomes. In this case, if we look at it, the only time we don't get at least one heads is when there's 3 tails. So 7 out of 8 chance. So going back to the definition of probability. So probability of any outcome of a chance process is a number between 0 and 1 that describes the proportion of times the outcome will occur in a very long series of repetitions. So a probability of 0 would mean that it would never happen. Okay. Probability of 1 means always happens. It's very rare to get a probability of 1 unless your sample space is like one thing and so that it always happens. And a probability of 0 can happen if it's not in your sample space. So the idea of probability seems straightforward. And what it does is it answers the question, what would happen if I did this many times? And usually nowadays when they're calculating new probabilities, a calculator or a computer does it for them. Not a lot of people do this by hand anymore, but it was done by hand many years ago. So randomness is predictable in the long run. That's a key thing here, is that we have to be talking about really long, we have to be talking about doing it many, many times. So unfortunately, that's not what most people do. Most people, our brains tell us that random things should also be predictable in the short run. So it's kind of similar to like if you have to 50-50 chance each time you have a kid that it's born a girl or a boy. And people like to say, oh, well, I've already had 2 girls, they're due for a boy. But that's not how probability works. Each time they have a kid, the probability is 50-50. It's not that, oh, if I have 2 girls, probability tells me I'm much more likely to get a boy. A lot of our brains try to tell us that, but we don't use that. So that's where this myth of the law of averages comes in. So future outcomes are not affected by past behaviors. Like I said, giving birth to 2 girls does not, mean that the next kid you have is going to be a boy. And going back to the myth of short run regularity, again, our probability does not allow us to make short run predictions. It's always based on long run things. So, and I just did this exact thing, women have a 50% chance of having a boy with each pregnancy. The gender of any previous children does not matter, except I used the example of a girl. So what computers do nowadays and what we used to do by hand a lot of the time is something called a simulation. So it's the imitation of chance behavior based on a model that accurately reflects the situation. Simulations are usually done with a table of random digits, a calculator random number generator, which we do have in our calculators. It's called randint, or computer software. Again, most of it is done using computer software nowadays. So there are 4 steps. There are 4 steps to performing a simulation. The first one is called state. And what you do is you identify the probability calculation. Okay, you then plan. So you describe how to use your chance process. Then you do. So this is where you actually perform the simulation. And we should state that we should do at least 20 trials. Okay. And then lastly, we conclude. So we use the results of the simulation to answer the question. So the nice thing is we don't have to run simulations every time we want to determine something because, you know, computer software and random number generators and our calculators help us do a lot of the work nowadays. So we're going to do an example. So we want to know, what is the probability that a student earns an 80% on a true-false quiz written in Chinese? Assume the exam taker does not know any Chinese. Should the instructor be concerned about cheating? So we want to know, how can we simulate the probability of guessing 80% correct on a true-false quiz? So I'm going to switch the table here. So we have some required elements we have to have. So when we do our do the state part, we have to identify our variable and have a statement of probability in either symbols or words. Our plan must include what tool we're going to use, what values we're assigning, how many values we're picking each time, how many times you're conducting the simulation, and what we're going to do about repeated or ignored digits and what we're recording. The do must include your simulation data if the number of trials is 20 or less, and a summary of the data if we're doing larger trials. And then our conclusion has to have a statement of probability, the answer to the question, and then usually when we're answering the question, we're talking about whether or not it's reasonable or expected or surprising or unlikely. Any of that information we'll do for our conclusion. So let's go ahead and run a simulation for that problem. So we want to know probability a student earns an 80% on a true-false quiz written in Chinese, assuming the test taker does not know any Chinese, and if the instructor should be concerned about cheating. So we want to perform a simulation using 20 trials. So let's start with the state part. So we want to find the probability of guessing %, of questions correctly on a true-false quiz. Okay, So it is important to note here that the probability you get a question correct is 50%. Because it's true, false, there's only 2 outcomes. So 50-50 shot. Okay. So there's a couple different ways we could perform our plan. If we wanted to use a table of random digits, we could do that. We can also use our calculator function, randint, to perform it, which is what I'm going to go ahead and do. So we're going to use the random number generator. Randint. We're going to let 0 represent an incorrect answer and 1 represent okay. So then our so then we'll run our trial 10 times, so n will equal 20. We'll record how many correct answers there were and how many incorrect answers there were. So now is the do part. So if you go to get to randint, you're going to get math. Then you're going to go to PRB or PROB depending on the calculator, and then you want number 5. Okay. I'm going to make so our min is 0, max is 1, n is our number of trials, which in this case is 20. And then you'll hit enter, and it'll give you a list of zeros and ones. And if you do this along with me, you're not likely to get the same responses as me. So looking at mine, so the number of correct, which are going to be the the ones, I got 11. And the number of incorrect, so zeros are 9. So that is a 55%. So that's an 11. An 11 out of 20, which is a 55%. So now it's time for the conclusion. So we can conclude. So our simulation that the probability of guessing correctly is 55%. This is much lower than 80% the student got. So we are a little concerned about cheating. I mean, 55 is, just in like 5 questions off from getting an 80, considering a 16 out of 20 is an 80. So, I mean, it's not as grievous as saying, like, if I had, in my simulation of 20, gotten 4 correct and then 16 incorrect, I would say the teacher should be very concerned about cheating. So, depending on what your simulation shows, there's not one correct answer for the conclude part, because it's all based on what your simulation shows. All right, so just to review, probability of an event is a number between 0 and 1. It's a long-run proportion of repetitions on which the event occurs. Something new. If all possible outcomes together must have probabilities that add up to 1. So if you take all of the probabilities in your sample space and you add them together, you have to get 1. So if we go back to our heads and tails, probability of landing on heads, 0.5. Probability of landing on tails, 0.5. Add them together, you get 1. The probability that an event does not occur is 1 minus the probability that it does occur. Which makes sense. Like if I say the probability that a coin lands on heads is 50%, in order to get to the remaining 50%, the probability it doesn't occur is 1 minus that. So referring to an event not A or not occurring is called a complement, and we denote it by whatever the event is called with an exponent of a C. So there's a couple different ways you can see this. So the probability of event A is 1 minus the probability of not event A. Or the probability of not A is 1 minus the probability of A. Or the probability of A plus the probability of not A equals 1. All 3 of those are the exact same thing. Every time the probability of our 2 events adds to 1. And you can have more than 2 events, but it's typical if we're talking about complements. You either have it or you don't. Okay. One other really important thing about probability is something called mutually exclusive. So if 2 events have no outcomes in common, the probability that one or the other occurs is the sum of their individual probabilities. So like probability of heads and tails is mutually exclusive. They don't have outcomes in common, so we can just add them together. When 2 events have outcomes in common, we refer to them as mutually exclusive or disjoint. So in other words, the probability of those 2 events is 0. So they cannot occur together. And it's easiest to talk about mutually exclusive events through examples, which is what we are going to do next. So we are rolling 2 fair 6-sided dice. One of them is red and one of them is white. And we have this lovely table here of all of the possible outcomes of our 2 different die, our red one on the left, our white one on the right. And we want to know the probability of rolling a sum of 5 or 2 even numbers. So I'm going to I'm going to denote my 2 events. So A is going to be rolling a sum of 5, and B is going to be rolling 2 even numbers. And I'm going to go through and I'm going to highlight in yellow event A and in green event B. So if I go through a sum of 5, so I know 4 plus 1 and 2 plus 3 is going to give me 5. So I'm looking for, I have 4 outcomes here. So a red 1 and a white 4, a red 4 and a white 1, and then the same thing with the 2 and the 3s. Okay. For 2 even numbers, I'm going to look through 2 even numbers. So 2 2s, 2 4s, and 2 6s. And that can happen, the red and then the white. It also happens with, so it can happen 2 2s, 2 4s, 2 6s. It can also be any combination of those. So a 2 and a 4 and a 2 and a 6, and then the reds and the whites. All right. So if we notice, there is no event A that is also in event B. There's no way to roll a sum of 5 using 2 even numbers. So these events are mutually exclusive. Okay. So I can just add their probabilities together. So the probability of A or B is the probability of A plus the probability of B. And in this case, the probability of A, rolling a sum of 5, was 4 out of 36, plus the probability of B, so 2 even numbers, is 9 out of 36, giving us a probability of 13 out of 36, which cannot simplify, so that is our final answer. So that leads us to our general addition rule for mutually exclusive events. The probability of A or B happening is the probability of A plus the probability of B. All right, so our next example. Online courses are rapidly gaining popularity among college students. Randomly select an undergraduate student who's taking an online course for credit and record the student's age, and we have a probability model. So we have 4 age categories. We have 18 to 23, 24 to 29, 30 to 39, and 40 or over. And we have the probability that a student in that age group is taking an online class. So the first thing we want to do is show that it's a legitimate probability model. So remember, all outcomes add to 1. So we're going to do 0.57 plus 0.17 plus 0.14 plus 0.12. And we get 1. So we're good. Okay. Next, we want to find the probability that the chosen student is not in the traditional college age group. So traditional college age group is 18 to 23. So we see the word not, we're going to think complement. Okay. And it is going to be mutually exclusive. Can't be in multiple age groups. So the probability of not college age is going to be 1 minus the probability they are college age. So that's going to be 1 minus 0.57, which is 0.43. Another way we could have done this is, okay, well, if I'm not in the 18 to 23 group, I'm in one of the others, so I could have also done 0.17 plus 0.14 plus 0.12. Both of them get you to the same value. All right, so we're going back to our 2 dice that we're rolling, the red one and the white one. And this time we want to know the probability of rolling a sum of 6 or 2 even numbers. So I'm going to go back and I'm going to get my 2 events. So A is going to be rolling a sum of 6. B is going to be rolling 2 even numbers. Okay. Going to use yellow for sum of 6 and green for my 2 even numbers. Okay. So rolling a sum of 6. 1 and 5, 2 and 4, and 3 and 3. So I'm going to highlight all of those. So 1 and 5, 2 and 4, 3 and 3. Okay. Now I'm going to go back and I'm re-highlighting my 2 even numbers. So we've got 2 and 2, 2 and 4, 2 and 6. 4 and 2, 4 and 4, 4 and 6, and then 6 and 2, 6 and 4, 6 and 6. And notice here, there were 2 times where I highlighted something that was already yellow. So that happened when I highlighted my 2 and 4 and my 4 and 2. Those are 2 even numbers that have a sum of 6. So these are not mutually exclusive. I have outcomes that appear in both events. So I can't just add my 2 events together. What I have to do is take the overlap because I don't want to add something twice. So the probability of A or B, so there are 5 ways to get a sum of 6 plus my 9 ways to get 2 even numbers, but 2 of those are counted in both. So I subtract 2 over 36 because I counted 2 of the events twice because they appeared in both groups. So I only need them to appear once. So I subtract the number of times. So I subtract them. So 9 plus 5 is 14, minus 2 gets us 12 over 36, which can simplify. And we get 1 out of 3. So that's one method. The second method is if we look at our table and we just found the number of outcomes that are either rolling a sum of 6 or 2 even numbers, we could have also counted the outcomes. And the 12 of our outcomes got highlighted. So if you have listed all of your sample space, you can always count them up if you're dealing with an OR situation. Or if you want to use the formula, you can use the formula. So then this leads us to the general addition rule. So this is for if 2 events are not mutually exclusive, the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. So again, don't want to count the overlap twice, so we subtract it. So if A and B are mutually exclusive, the probability of A and B ends up being 0, which is how we get that general addition rule for mutually exclusive events. And that's what we got on the previous page. Okay. Another very common example is examples containing decks of cards. Okay. So a card is selected at random from a deck of 52 cards. So a deck of cards has 52 cards. Determine if the following events are mutually exclusive and then find the probability of the events. So there are two different colors in a deck of cards. There's red and there's black. There are 4 different suits. There is clubs, spades, hearts, and diamonds. Okay, so that's what we have in this picture. We have ace to king in clubs. So this is clubs. For those of you that don't know much about cards. Then we have 2 to king in spades. Sorry, ace to king. Ace to king in hearts. And then ace to king in diamonds. Okay, so there's 52 total cards in the deck. Each suit contains 13 cards because there's 4 suits and they're evenly split up. So the first one is the probability of getting a red or a queen. So first we have to determine, are these mutually exclusive? So basically, can I draw a red queen? And the answer is yes. So they are not mutually exclusive, which I'm going to abbreviate. So we have to do the probability of red plus the probability of a queen minus the probability of a red queen. So half the deck is red, 26 out of 52, plus queens, which there are 4 of, minus the number we counted twice for being red queens, which is 2 out of 52, which 26 plus 4 is 30, minus 2 is 28 out of 52. Which in simplified form is 7 out of 13. It is okay here if you put decimals, because I realize 28 out of 52, 7 out of 13, not fractions we typically deal with. So if you're going to do a decimal, I prefer 3 decimal places just to be accurate. So you can also think of it as 0.538, so about a little over 50% chance that if you draw a card from a deck, it'll be red or a queen. Okay. Next, we want to look at the probability of getting an ace or a king. So these are mutually exclusive. A card cannot be both an ace and a king at the same time. So I can do the probability of an ace plus the probability of a king. There are 4 aces. There are 4 kings. So we get 8 out of 52. Which becomes 2 out of 13. Which again, if you want to think in terms of decimal, 0.154. Oh, not a very high chance. That one's about 15%. Not a very likely event that you will draw a ace or a king. All right, next we're looking at the probability of a queen or an even number. So something cannot be a queen and even, so these are mutually exclusive. So we can do the probability of a queen plus the probability of an even number. So there are 4 queens, and the even numbers are 2, 4, 6, and 8. 2, 4, 6, 8, and 10. So there are those 5 cards in each of our 4 suits, meaning we'll have 20 out of 52 of those, giving us 24 over 52, which is the fraction 6 over 13, which is about 0.462, so 46%, little under 50%, so still a pretty high chance. Okay. The last probability we're going to look at is the probability of getting a black card or an odd number. So these are not mutually exclusive. I can draw a card that is black and odd, so we're going to have to subtract some overlap. So probability of black plus the probability of an odd number minus the probability of a black odd number. So half the deck is black, so 26 out of 52, plus our odd numbers in this case are 1, 3, 5, and 9. So there's only 4 odd numbers across the 4 suits, so that's 16 out of 52. And then we have to do our odd black numbers, so that's going to be 8 of the cards. So 26 plus 16 minus 8 is 34 over 52, which is 17 out of 26, which is 0.654. So very good chance that, about 65%, that if you draw a card, it's black or odd. So of the 4 probabilities we calculated here, the one that was that's most likely to happen is our black or odd, followed closely by red or queen. In our next example, students in an urban school were curious about how many children regularly eat breakfast. They conducted a survey asking, do you eat breakfast on a regular basis? All 595 students in the school responded to the survey. The resulting data are shown in the two-way table below. So we've got our male and our female column and our totals, the number who eat breakfast regularly, don't eat breakfast regularly, and our total. So important thing to remember here is the 595 is our sample space. Okay, we have different totals for who eat breakfast regularly and don't, and we have different totals of males and females, but both of those totals have to add to our sample space of 595. So looking at our first probability, if we select a student from the school at random, what's the probability that the student is a female? So we are going to look at the total for our female column, which is 275 over our sample space, 595. So 275 over 595, decimal, fractions this big, you can write a decimal, 0.462. Next, we want to know the probability of someone who eats breakfast regularly. So probability eats breakfast. I'm just going to abbreviate that. I'll write breakfast. So total number of students who eat breakfast regularly, 300 over our sample space, 595. So 300 divided by 595 gives us 0.504. Okay. Next, we want the probability of a female who eats breakfast regularly. So that's probability of female. And eats breakfast. So if we look at our table, we go to female and eats breakfast, we get 110 out of our total number of students, 595. And we get 0.185. So not a very high probability. Next, we're looking at a female or eats breakfast regularly. So key difference here is the or. Now, we know that you can be a female who eats breakfast regularly, so it's not mutually exclusive. So we're going to do the probability of female plus the probability you eat breakfast minus the probability you are a female and eat breakfast. So probability of being female, 275 over 595. Plus the probability that you eat breakfast, 300 over 595. Minus the probability you are a female and you eat breakfast, 110 over 595. All right, so 275 plus 300 minus 110 gives us 465 over 595, which is 0.782. There's a very good chance that if I randomly asked a student in the school, randomly picked a student in the school, I should say, they're going to be either female or they eat breakfast regularly. Okay. Last example we have is on hair and eye color of a group of women. We have the hair colors of brown, blue, hazel, and green, and the hair colors of black, brown, red, and blonde. So we don't have any of our totals here. So first thing we want to do is find the total in the sample space, which we end up getting 313. So you have you can just literally add all of the numbers together. And that's how you'll get the total. So we're going to randomly select one woman. We want the probability that she either has red hair or green eyes. So again, these are not mutually exclusive events. You can have red hair and green eyes because we look in the table. We go to red and green. It's not 0. There's a number there. So we're going to do the probability of red hair plus the probability of green eyes minus the probability of red hair and green eyes. So probability of red hair. So I'm going to have to add that row together. So 16 plus 7 plus 7 plus 7 gives us 37 out of the 313, plus the probability of green eyes, so 2 plus 14 plus 7 plus 8 is 31 out of 313, minus having red hair and green eyes, which is 7 out of the 313. So 37 plus 31 minus 7 gives us 61 out of 313, which is 0.195. So almost 20% chance. Okay. Next, we want probability she has red hair and green eyes. Well, we had to find that to do our last problem. So that was our 7 out of 313, which is 0.022. So about a 2% chance, not a very high probability. So I know this was a lot of information in one video. Please reach out if you have any questions. I'll be going over some more stuff in class. We'll be working on an assignment over this, but please feel free to reach out and ask questions over anything you are unsure about.